So first of all, I'd like to thank the faculty for the opportunity they give me to spend this year here at the Institute, and also for the opportunity of giving this short presentation. So my purpose today would be to talk about this phenomenon of growth of high Sobolev norms in the case of some nonlinear Hamiltonian PDEs, and more specifically, in the first part of the talk, I'm going to speak about Schrodinger equation, and in the second part of the talk, I'm going to speak about a nonlinear half-wave equation. So let me start with the Schrodinger equation. I'm taking the defocusing cubic NLS, where the solution here, u depends on time, which is a real variable, and on x, which is either in r to the d or t to the d, and is complex valued. This is a Hamiltonian equation corresponding to the energy that I define here, and as a consequence, the energy is conserved. So the energy of the solution at time t coincides with the energy of the initial condition. The same is true for the mass. And now you notice that if we put together the energy and the mass, it follows that the Sobolev norm h1 will be uniformly bounded in time. And actually, if you are in dimension 1, the same is true for any integer Sobolev norms, because in dimension 1, the Schrodinger equation is completely integrable. So then let's go to a higher dimension, say dimension 2, NLS on the torus T2, which will be my model for this first part of the talk. First of all, we know that this equation is globally well posed in HS as greater or equal to 1. And by this, I mean that if you start with an initial condition in HS, then there exists a unique global in time solution which stays forever in this Sobolev space. And now it's natural to ask ourselves what is the fate of these global solutions as we make time go to infinity. In order to address this question, in a first step, Professor Bourgain and Stafilani, and later on others, proved that we have this kind of polynomial upper bounds on the Sobolev norms of the solutions at time t. So in particular, you notice that as soon as we are with an s strictly greater than 1, this bound is actually going to infinity when time goes to infinity. So naturally, the further question would be, is there actually an example of a solution which has this growth property, Sobolev norms that grow to infinity over the time? And if such an example exists, then what would be the growth rate? And the conjecture of Professor Bourgain would be that this growth rate is t to the epsilon for any positive epsilon. Okay? So now, to make things clear, we don't have any answer available for these questions, and obviously nor for the conjecture. But there are significant partial results that I'm going to talk about in a few minutes. So all
these questions are taking place on a torus, right?
Yeah, everything is on the torus T2.
Rn, there's no problem.
No. For R2, we have scattering, which means solutions that nonlinear solutions are close to linear solutions, so there nothing happens.
It's because you're in a compact domain, the waves can go in.
Exactly. Yeah. We don't have the decay as time goes to infinity. So before telling you about the mathematical results, let me tell you about something about the physical relevance of this growth of high Sobolev norms. So the reason why we are interested in such a property is because it captures what is called the forward energy cascade. So in physics, or more specifically in the weak turbulence theory, what this means is that you have some nonlinear system, and you see how your energy moves from lower frequencies to higher and higher frequencies over the time. And if you have growth of high Sobolev norms, it's very easy to see that this energy cascade takes place. So it's just sufficient to write your Sobolev norm on the Fourier side. So if you want this quantity here to grow, but in the same time keeping the mass constant, then the only possibility is that this psi to the s grows. Or in other words, this Fourier transform of u has to be supported on larger and larger xi's as you increase the time. And this is nothing else than the forward energy cascade. Now, if you want to interpret this not on the Fourier side, but on in the physical space, what this means is that your dynamics will move to smaller and smaller scales. And there we can imagine that a chaotic behavior may occur in the end. So here are the partial mathematical results. Since I don't have time, I'll just say that so the first results are by Professor Bourgain, Kuxin, Zaher Hani, Guardia Kaloshin. And I'm going to focus on this result of Colliander, Kills, Tafilani, Takaoka, and Tao, which is what we call the finite time growth of high Sobolev norms. So more precisely what they proved in the context of this Schrodinger equation on the torus T2 is that if one is given with a very small constant epsilon and a very large constant k, then they are actually able to build a solution which at time 0 is smaller than epsilon and at a later time t is larger than k. Their construction is quite impressive, and actually all the works that followed, all these 3 papers mentioned here, are based on their construction. However, the drawback of this result is that we don't know what happens after this time t. So the solution might very well keep growing and eventually reach infinity, or it might as well become small again, or it may have any other behavior in between. And maybe let me finish this brief presentation of the Schrodinger equation with this result of Hani, Posader, Tsvetkov, and Visilia, which was recently announced, but there's not yet a preprint available for it. So what they claim to have proved is that they can actually prove an infinite time growth, not for NLS on this torus T2, but on R cross T to the power D. And I don't know much about this result, but it seems that what helps them here is the fact that they have some extra decay coming from the R component. OK, so let me now continue with the second part of this talk, which is about the cubic half-wave equation written here. So I'm considering this equation on R, and absolute value of D here is simply a non-local operator corresponding to multiplication by the absolute value of the frequency psi on the Fourier side. So this is an equation which appears in physics, in gravitational collapse, and other things. And it is also in the same family as one-dimensional models of weak turbulence considered by Maida, McClory, and Tabak. So they actually considered this type of equations with alpha strictly smaller than 1, while here we have alpha equal 1. The equation is globally well posed in HS, S larger or equal to a half. And the main result I wanted to present you today is a CKSTT type of result for this cubic half-wave equation. It's stated here, and essentially it says that if we are given with a very small constant delta, then we can build a solution smaller than delta at the initial time and larger than 1 over delta at a later time. And we know exactly what this time is. And what's important is that it's exponentially in 1 over delta. Okay, so I'm going to spend the rest of this talk trying to show you how I got to this result.
Can I ask you, so if
Yeah.
you have times less than exponential, then you know what doesn't go there, doesn't get big.
Yes.
You need that, at least that time to get.
Yes. So this is the kind of Nekoroshev type theorem you're referring to. So the first natural thing to do is to actually, instead of looking at your whole half-wave equation, to look at the resonant dynamics of this equation. And to get this resonant dynamics, actually in this case, you only need to solve this simple system of 2 equations. So here the absolute values comes from the fact that I have absolute value of D in my equation. And then these alternated sums come from the fact that I have a cubic nonlinearity and one of the factors has a conjugate. So this is the So you have this system, and it's very easy to see that the only solutions of the system are when all the 4 frequencies have the same sign, either all positive or all negative. So if you take the case when they are all positive, then what you get is that the resonant dynamics is actually given by this equation here, with pi plus being the projection onto non-negative frequencies. This is an equation called the Zebu equation. It was introduced rather recently in 2008 by Patrick Gérard, who was my PhD advisor, and Sandrine Crelier. And its name comes from the fact that this projector pi plus is sometimes called the Zebu projector. Now, since this is the resonant dynamics, we can prove some kind of approximation result, which says that if you start with certain data, which are small, of order epsilon, then the solution for the wave equation will stay close to the solution for the Zebu equation for a long time. And this time is given here. What's important here is that 1 over epsilon squared is actually the time at which you start seeing the nonlinear effect. So with respect to that, you just gain this log of 1 over epsilon. So it's a long time, but it's not very long either. OK, so now let me shift your attention from this wave equation to the Zebu equation and tell you what are the main properties of the Zebu equation. So first of all, it's still Hamiltonian. If we look at it in the space L2+, L2+ is the space of L2 functions, but which have only, which are supported only on positive frequencies. And we can also see this as a Hardy space of holomorphic functions in the upper half plane. Now, in terms of Sobolev norms, we can easily prove that the Sobolev norm H1/2 is uniformly bounded in time, and we have global well-postedness in HS for any s greater or equal to 1/2. The interesting property of the Zebu equation is that it is completely integrable, in the sense that Gérard and Grelier found a Lax pair for it. And this Lax pair is given in terms of, let's say, the main operator in the Lax pair is a Henkel operator that I define here. So since we have an integrable equation, we know that we're going to have an infinite sequence of conservation laws, which are related to the spectrum of this operator, but we can build other conservation laws. And for example, we can show that this L2 norm of HPs applied to U are conservation laws. And it's easy to see that these conservation laws are actually at the level of the LP norms. And if you use some Sobolev embedding, you see that they are all weaker than the H1/2 norm, which we already knew it's controlled. So it's a rather atypical situation, at least if we compare it to the situation of the Schrodinger equation, where we have an integrable system with infinitely many conservation laws, but they don't tell you anything about the higher Sobolev norms. They're all controlled by the H1/2 norm. So to actually get some information about the higher Sobolev norms, you need to work more. You need to find an explicit formula for your solution. And based on this explicit formula, the result I was able to prove is the following. Indeed, we have infinite time growth for this Zebu equation. More precisely, if you take, say, this simple initial condition, then you can explicitly write what your solution is. It decomposes as this sum. The first term is innocent, while the second term has a pole with imaginary part 1 over t squared. So you have a pole which is supposed to be in the lower half plane, and as time goes to infinity, this pole approaches the real line. Or in other words, your radius of analyticity goes to 0. And this is exactly what gives you the growth. So now if you make a small computation, you see that the solution grows like t to the 2s minus 1 in the HS norm. And now what is so special about this very simple initial condition? Well, if you look at the corresponding Henkel operator, it has a double eigenvalue. And actually, whenever we have, say, a finite rank Henkel operator with a double eigenvalue and all the other eigenvalues simple, you always have this growth phenomenon. So it's always related to the multiplicity of eigenvalues slash the radius of analyticity going to 0. So let me make a small parenthesis here and tell you that if instead of looking at the Zebu equation on the torus, you look at it on the real line, sorry, you look at it on the torus, there you have a completely different behavior. So there's a recent preprint of Gerard and Grelier in which they prove that on the torus, all solutions are quasi-periodic. So in particular, you don't have any unbounded orbits there. Okay. So finally, let me finish by just briefly telling you how we go from the Zebu equation back to the half-wave equation. So first of all, using the growth for Zebu and the approximation, we get a relative growth for the wave equation in the sense that from epsilon, we can reach epsilon times this log. Of course, this is still very small if epsilon is small. But now, you can use a very cheap trick, which is the scaling invariance of the equation. So this equation is L2 critical. Then if you rescale it by a factor which is in between epsilon and epsilon times the log, then you get indeed this arbitrary large growth in the CK-STT spirit. So finally, let me finish with two comments. There's a work in progress going on with Gerard, Lensman, and Raphael, where we're trying to investigate the saturation of the growth of Sobolev norms. So we're trying to see what happens after this growth time. So essentially what we want to prove is that the Sobolev norms will not become small again. They will stay at some, they will not go to infinity either, but they will stay large. And then finally, once we have all this information about this half-wave equation, the natural open question would be to now go to the other models from Maida, McLaughlin, and Tabak and see if there we can rigorously prove this growth of high Sobolev norms. So I will stop here. Thank you for your attention.